Welcome, curious minds, to another deep dive. Today, we're tackling an element that might seem incredibly simple, just one electron, right?
Yeah,
But it holds a universe of complexity and surprise. We're talking about hydrogen,
that's right. The most abundant element, absolutely crucial for life.
and often hailed as the fuel of the future. We hear that a lot.
We certainly do.
Our journey today is inspired by Chapter 10 of Shriver and Atkins Inorganic Chemistry, the 5th edition, a fantastic resource. Think of this deep dive as, well, your audio shortcut to getting really well informed about hydrogen's fascinating chemistry. Our mission is basically to guide you step by step through hydrogen's fundamental properties, how it behaves, and its huge role in, well, everything from energy to biology. We'll try to simplify the complex bits, explain the technical stuff, and help you connect the dots, without needing the textbook open right in front of you.
Exactly. And what's truly astonishing here, I think, is how an element with such a basic atomic structure, just one S1, can display such a diverse range of chemical personalities. It can act as both a strong acid and a strong base. It forms these unique bonds that are literally foundational to life itself. Let's unpack the secrets of this remarkable atom.
Okay, let's start with the basics then. Hydrogen, element number one, simplest atom, right? But don't let that fool you. It's the most abundant element in the entire universe.
Absolutely. Though here on Earth, it's a bit different. It's so light, it tends to, escape our atmosphere over time.
Ah, right. A bit of a flight risk. So what we do find is locked up.
Precisely. Locked up in water, minerals, all living things. And usually it's found as dihydrogen, H2. Two hydrogen atoms bonded together.
And this dihydrogen H2, it has an incredible array of uses. We see it everywhere.
We do, from making fertilizers like ammonia, plastics.
To producing metals, powering rockets. I mean, it's versatile.
Very. It's even a natural byproduct of fermentation in biological systems.
And that fuel of the future tag comes because when it reacts with oxygen, it just produces water.
Exactly. Water is the only product. H2 plus O2 gives H2O, which is why it's so appealing environmentally.
But there's a catch.
There's always a catch. The big challenge is storage. How do you store this very light, very volatile gas efficiently and safely? That's the multi-billion-dollar question.
Okay, so how does this single atom behave chemically? You said it's flexible.
Incredibly flexible. Despite just having that one electron, its 1s1 configuration, hydrogen forms compounds with almost every other element. It's quite sociable. And it can swing both ways, chemically speaking. It can gain an electron to become the hydride ion, H. Here, it's acting as a strong Lewis base, an electron pair donor.
H minus the hydride ion.
Right. And this ion is quite squishy, we sometimes say. Polarizable. Because its two electrons are only held by one proton, their cloud is easily distorted. Its size actually changes depending on what it's bonded to.
Okay, so that's H minus. What about the other way?
The other way is losing that electron, becoming H plus A, the proton. Essentially just a bare positive charge with an incredibly tiny radius. This makes it a very strong Lewis acid and electron pair acceptor. It's so reactive that in condensed phases, like water, it's never truly alone. It's always associated with a Lewis base, like H3O plus A.
Which is fundamental to all acid-base chemistry, right?
Absolutely fundamental. That proton transfer is key.
That flexibility really highlights hydrogen's unique position.
And speaking of unique, what about its isotopes? You mentioned those earlier.
Ah, yes. The isotopes. This is crucial. Hydrogen isn't just one thing. It has three main forms. There's the most common one, protium, just regular 1H. Then there's deuterium, 2H or D, which has a neutron, so it's about twice as heavy. And finally, radioactive tritium, 3H or T, with two neutrons.
Protium, deuterium, tritium. Got it. And the mass difference matters. Oh, significantly. The mass difference between protium and deuterium is huge, percentage-wise. This leads to measurable effects in reaction rates. We call it the kinetic isotope effect. If you swap a hydrogen for a deuterium in a molecule, the rate at which a bond involving that atom breaks can change noticeably.
Why is that useful?
Well, it's a powerful tool for chemists. It helps us figure out how reactions happen, the mechanism. If the rate changes significantly when you swap H for D, it strongly suggests that breaking that specific bond is involved in the rate-determining step of the reaction.
Clever, like leaving a little breadcrumb trail.
Kind of, yeah. And another key property is nuclear spin. The nucleus of protium, the proton, has a spin. This is the basis for NMR spectroscopy.
NMR, nuclear magnetic resonance. That's huge in chemistry, especially organic.
Absolutely huge. It allows us to map out the structure of molecules containing hydrogen. We can see what kind of environment each hydrogen atom is in. It's indispensable for everything from simple molecules to massive proteins.
So this unique character, being able to act like an alkali metal sometimes or a halogen other times, but not quite fitting either. That's why it sits alone on the periodic table.
That's exactly it. It has one valence electron, like group 1, but its ionization energy is way too high to be a metal under normal conditions. It needs one electron to fill its shell, like group 17 halogens, but its electron affinity is much lower. It really is in a class of its own.
Okay. And the H2 molecule itself,
Yeah.
dihydrogen, you said it's stable.
Very stable. The HH apt is quite strong. High bond enthalpy makes the molecule relatively inert at room temperature.
So not just spontaneously reacting with everything.
Definitely not. But that doesn't mean it's inactive. It just needs a little push, an activation energy boost. Reactions involving H2 usually need a catalyst, or maybe UV light, or high temperature to initiate radicals. We'll explore these activation pathways a bit later.
Okay, great. So let's dive deeper into the compound's hydrogen forms. You mentioned broad classes before. Let's get into the details now.
Right. We generally talk about molecular hydrides, saline hydrides, and metallic hydrides, plus some more specialized complexes. Let's start with the molecular ones.
Molecular hydrides. These are the ones with covalent bonds.
Right.
Usually with p-block elements like carbon, nitrogen, oxygen.
Exactly. And beryllium, too, interestingly. These are typically discrete molecules, and we can even subcategorize them based on how the electrons are distributed.
Okay, how does that work?
Well, think about the valence electrons on the central atom, the E in EHN. If all those valence electrons are used up making normal two-center, two-electron bonds and there are no lone pairs left over, we call it electron precise.
Like methane. CH4, carbon has 4 valence electrons, makes 4 single bonds to hydrogen. No lone pairs.
Perfect example. Methane, silane, SH4. Their shapes, like tetrahedral for methane, are nicely predicted by VSEPR theory, just electrons pushing each other as far apart as possible.
Okay, electron precise. What else?
Then you have electron-rich hydrides. Here, the central atom has more electron pairs than it strictly needs for bonding. In other words, it has lone pairs.
Ah, like ammonia, NH3, with 1 lone pair. Or water, H2O, with 2.
Exactly right. Ammonia is trigonal pyramidal, water is angular or bent again. VSEPR helps us predict these shapes based on minimizing repulsion, including from the lone pairs.
Makes sense. And the third type sounds intriguing. Electron deficient.
Yes, this is where things get really interesting chemically. These compounds simply don't have enough valence electrons to form traditional two-center, two-electron bonds for all the connections.
How do they cope?
They get creative. They often associate forming larger structures using unconventional bonding. The classic example is diborane, B2H6.
Diborane. Right. Boron chemistry is known for being a bit weird.
It is. If you try to draw a simple Lewis structure for B2H6, you find you need 14 electrons, but you only have 12 available.
So what happens?
It forms 3 center, 2 electron bonds. You have 2 boron atoms and a hydrogen atom in between, but only 2 electrons are shared across all 3 atoms. These are called bridging hydrogens, BHB bridges.
Wow. 2 electrons holding 3 atoms together.
It's quite remarkable, and this tendency is why boron hydrides often form larger clusters or polymers. Aluminum hydride, AlH3, does something similar, forming a polymer network.
Fascinating stuff. And how do these molecular hydrides typically react?
Well, it often comes down to the polarity of the EH bond. If the electronegativity of element E and hydrogen are similar, like in many hydrocarbons, the bond might break evenly homolytic dissociation, forming radicals. EH becomes E plus H.
Some of your radicals.
But if E is much more electronegative than hydrogen, think oxygen, fluorine, chlorine, then the bond is very polar, with hydrogen being partially positive. These compounds tend to act as Brunstad acids. They readily donate that proton H plus ol.
Like water, HeCl, HF. Acidity increases across a period and down a group generally.
Generally, yes. Across a period, electronegativity pulls electrons away from H more. Down a group, the EH bond gets weaker and longer, making the proton easier to release.
And the opposite scenario, if E is less electronegative than hydrogen.
Then hydrogen pulls the electrons more strongly, becoming partially negative. We say it has hydridic character. These compounds can act as hydride ion H donors.
Like the reducing agents you mentioned, NaBH4.
Exactly. Sodium borohydride, NaBH4, and lithium aluminum hydride, LaRaL-LH4, are prime examples. They deliver H ions in reactions, which is incredibly useful for reducing various functional groups in organic synthesis.
Okay, this is a good place to pause on specific compounds and talk about something that connects many of them, especially the electron-rich ones like water and ammonia. Hydrogen bonding. This seems really important.
Oh, it's fundamentally important. It's a special type of intermolecular force. It happens when you have a hydrogen atom bonded to a very electronegative atom, typically nitrogen, oxygen, or fluorine. That bond is highly polar, leaving the hydrogen with a significant partial positive charge, F+. This partially positive hydrogen is then strongly attracted to a lone pair of electrons on an electronegative atom, Nl or F, on a neighboring molecule. That attraction is the hydrogen bond.
So it's like a bridge between molecules mediated by hydrogen.
A sort of electrostatic bridge, yes. And although a single hydrogen bond is much weaker than a covalent bond, maybe 5–10% of the strength they add up.
And the evidence is in things like boiling points.
Absolutely striking evidence. Compare water, H2O, with hydrogen sulfide, H2S. Oxygen and sulfur are in the same group. H2S is heavier, so you'd expect it to have a higher boiling point.
But it doesn't. Water boils at 100 degrees C. H2S boils way down at negative 60 degrees C.
Exactly. The difference is the extensive network of hydrogen bonds in water, holding the molecules together much more strongly, requiring more energy to separate them into gas. Same story for ammonia, NH3 versus phosphine, PH3, and hydrogen fluoride, HF versus hydrogen chloride, HCl.
And this isn't just about boiling points. It's crucial for life.
Immense biological importance. Hydrogen bonding is responsible for the open lattice structure of ice, which makes ice less dense than liquid water. That's why ice floats. Crucial for aquatic life. It's key to maintaining the specific three-dimensional shapes of proteins, which dictates their function. Enzymes wouldn't work without it.
And DNA, the double helix.
Held together by hydrogen bonds. The specific pairing adenine with thymine, AT, guanine with cytosine, GC, relies on specific patterns of hydrogen bonds between the base pairs. This is the basis of genetic information storage and replication. Without hydrogen bonds, life as we know it wouldn't exist.
Wow, such a subtle interaction with such profound consequences. Can we detect them?
Yes, spectroscopically. Hydrogen bonding affects the vibrations of the EH bond, so you see characteristic shifts and broadening in infrared IR spectra. It also affects the chemical environment of the proton, leading to distinct signals in proton NMR.
Incredible. Okay, let's move on to the next major class. Saline hydrides. These are the ionic ones.
That's right, formed between hydrogen and the most electropositive elements, mainly the group 1 alkali metals like Li-H, Na-H, and the heavier group 2 alkaline earth metals like KH2, SRH2, BH2. These are essentially ionic solids, like salts. They consist of metal cations, like Na+, and hydride anions, H. They typically form crystalline structures, like the rock salt structure for NaH.
And you mentioned earlier that H is confirmed by electrolysis.
Yes, if you melt these saline hydrides and pass an electric current through the melt, you collect hydrogen gas, H2, at the anode, the positive electrode. This shows that a negative hydrogen-containing species, H, must have migrated there and been oxidized.
Makes sense. Are they stable?
They are solids, non-volatile, but they react very vigorously, sometimes dangerously, with water or other proton sources releasing H2 gas. NaH plus H2O gives NaOH plus H2. That can be quite exothermic.
So, useful but handled with care. What are they used for?
Primarily as strong bases and as sources of the hydride ion H in chemical synthesis, they're powerful reducing agents. They can be used in metathesis reactions to introduce hydride into other compounds. For example, reacting a Li-H with 6L4 can produce silane, HAH4.
And you mentioned magnesium hydride MgH2 for hydrogen storage, even though magnesium is group 2.
Yes, MgH2 is interesting. It's somewhat intermediate between saline and covalent, but it's often grouped here. It's being heavily researched for hydrogen storage because it can pack a lot of hydrogen by weight and volume, and the reaction MgH2 equals Mg plus H2 is reversible, although it requires fairly high temperatures.
Okay, that covers saline hydrides. What about the third main group, metallic hydrides?
Right. These are formed when hydrogen reacts with many of the D block and F block transition metals. They often look metallic, conduct electricity.
But they're different from the parent metal.
Yes, usually less dense, more brittle. And a key feature is that they are often non-stoichiometric.
Meaning the ratio of metal to hydrogen isn't a fixed whole number, like ZrHx where X can vary.
Exactly, like ZrH 1.30 to ZrH 1.75. We often think of the hydrogen atoms occupying interstitial sites, small holes within the metal's crystal lattice. The electrons from hydrogen typically go into the metal's delocalized conduction bands.
Which explains why they still conduct electricity.
Generally, yes, although the conductivity often changes as you add more hydrogen.
Now, you mentioned a hydride gap. Some metals don't play ball.
That's right. There's a region in the middle of the D block, groups 7, 8, and 9, think manganese, iron, cobalt, ruthenium, osmium, etc., that generally don't form stable binary hydrides under normal conditions. This is known as the hydride gap.
But wait, iron and nickel and platinum are used as catalysts involving hydrogen all the time. Hydrogenation catalysts.
Excellent point. And that's the key distinction. While they don't form stable bulk hydrides easily, their surfaces are very good at interacting with and activating H2 molecules. They absorb H2, often breaking the HH bond, making the hydrogen atoms available for reaction. So they are crucial catalysts, even if they don't fit the metallic hydride definition in the bulk sense.
Ah, okay. Surface chemistry versus bulk compound formation.
Precisely. Palladium is a famous exception near the gap. It does form a stable bulk hydride, PDHX, where X can get close to 1. It can absorb huge volumes of hydrogen gas, up to 900 times its own volume.
The hydrogen sponge, I've heard that term.
That's the one. This property has led to its use in hydrogen purification. Impure H2 gas is passed over a thin palladium membrane. Only hydrogen atoms can diffuse through the metal lattice, emerging as pure H2 on the other side.
Clever. And the storage ability is used in batteries, too.
Yes, nickel metal hydride, Nomea batteries, are a good example. They use special metal alloys, often intermetallic compounds like Lana-5, that can reversibly absorb and release hydrogen electrochemically. The reaction involves forming metal hydrides at the cathode. They're a rechargeable, less toxic alternative to older NiCad batteries.
Okay, so beyond these three main classes, molecular, saline, metallic, you also mentioned specialized complexes.
Yes, particularly in organometallic chemistry and catalysis. We talk about hydridoligands and dihydrogen ligands.
Hydridoligand, that's just the H ion attached to a metal center.
Essentially, yes. H acting as a ligand, donating its electron pair to the metal. It's considered a soft, 2-electron sigma donor. Many transition metal complexes feature hydridoligands. Even metals within that hydride gap can form complexes containing H. The character of this bound H can vary. Sometimes it's more protonic, at plus, sometimes more hydridic, depending on the electronic nature of the metal center and the other ligands attached. H can even bridge between two metal atoms in some complexes.
And dihydrogen ligands, that's the whole H2 molecule sticking to the metal.
That's right. The intact H2 molecule can coordinate side-on to a metal center. It donates electron density from its bonding sigma orbital to the metal, and importantly, it can accept electron density back from the metal into its anti-bonding sigma star orbital. This is called the back donation.
Like how carbon monoxide binds to metals.
Similar principle, yes. It's a synergistic bonding interaction. And if the metal is electron-rich enough, this back donation can weaken the HH bond so much that it actually breaks, leading to two separate hydridoligands. We call that oxidative addition.
So the metal complex literally pulls the H2 molecule apart.
It can, yes. The first structurally characterized example was a tungsten complex, WCO3H2, PyPr32. It's even possible to have both hydrato-H and dihydrogen H2 ligands on the same metal simultaneously. These complexes are crucial intermediates in many catalytic hydrogenation processes.
Okay, we've covered a lot of ground on what hydrogen compounds exist. How do chemists actually make them? Are there general strategies?
There are. While just reacting the elements together, direct combination or hydrogenolysis, 2E plus H2EH, works for very stable hydrides like ammonia or sodium hydride, it often requires high temperatures, pressures, or catalysts because the H2 bond is strong.
So what if direct combination isn't feasible?
Then we look for other thermodynamically favorable routes. One common method is protonation of a Bronsted basic anion. If you have a very basic anion like the nitride ion N3 and Le3N, reacting it with a proton source like water will generate the hydride. Li3N plus 3H2O gives 3 Li weights plus NH3.
Basically using a strong base to rip a proton off water.
Pretty much. The water acts as the acid here. Another very important method is metathesis, which usually involves swapping a halide ion for a hydride ion.
Metathesis, like an exchange.
Exactly. You take a metal or non-metal halide, like CCl4, and react it with a good hydride donor, like LiLH4. The hydride ion effectively displaces a chloride ion. So LiLH4 plus CCl4 can give you CiH4 plus LaLAl4.
And the strength of the hydride donor matters.
Very much. Simple saline hydrides like LaLH or NaH can work, but complex hydrides like lithium aluminum hydride, LaLH4, are much stronger hydride donors than, say, sodium borohydride, NaBH4. Choosing the right reagent is key for synthesis.
Wow, what a journey, seriously, from just that simple 1s1 electron configuration
Right.
to its complex role in potential fusion energy, these vital biological cycles, advanced materials like metal hydrides. Hydrogen truly is the essential element, but in so many different ways. We've seen how its isotopes behave differently, how we make H2 from labs to massive industrial scales, and all these fascinating ways it forms compounds. Molecular, saline, metallic, those intricate metal complexes.
And don't forget hydrogen bonding.
Oh yeah, the hidden force. That invisible scaffolding that literally sculpts our world and, underpins life itself. It's amazing. What really stands out to me time and again is that hydrogen's chemistry is anything but simple. It's a unique spot on the periodic table. It's different ionic forms, H
Yes.
plus and H. It's absolute necessity in biology, and all this potential as a clean energy carrier.
Yeah.
It all stems from those fundamental atomic properties.
It really does. And if we try to connect this to the bigger picture, maybe a final thought, hydrogen's sheer versatility is quite profound. Its ability to act in so many different chemical roles, tiny proton bridging ligand, gas, part of a solid metal lattice. It really forces us to question any easy assumptions about simplicity in chemistry. It's a constant reminder, I think, that often the most fundamental building blocks hold the deepest complexities. And, the ongoing quest for better hydrogen storage, driven by the need for a sustainable energy future, just underscores how relevant and important this simple element continues to be.
A perfect thought to end on. The simplest can be the most complex. Thank you so much for joining us on this deep dive into the chemistry of hydrogen. We really hope you've gained some valuable insights.
Hope it was helpful.
And as always, we hope you feel inspired to explore further. Thanks for listening.